Evening, ma'am.
Okay, Ali, can you tell me what was the last topic?
Dehydration of alcohol.
Okay, dehydration. Okay, so I think we have done till here. Dehydration of alcohol. Okay, now let's understand the mechanism for the dehydration of alcohol. Okay, so sometimes in your exam they just give you the reaction, okay, and they will ask you to write on the mechanism. What is the mechanism for this reaction? Hello, Rimdha, how are you?
Hello, ma'am. I'm good.
Okay, so Rimdha, you have your pre-board, first pre-board on 15th November, right?
No, ma'am. Chem is on December 4th.
Okay, it's on 4th December. First pre-board, right?
Yes.
Okay, so till now we have only completed your only two chapters, and the third chapter is basically it will be completed like today or like tomorrow, like in 2 days, after 2 3 days. Now your attendance is very short, Rimda. Why you are not joining regularly?
Ma'am, I've been joining like the last week and all, like regularly, but like before that, I was sick and then I was busy with stuff.
Okay, okay, so no problem, no issue. But please try to join regular on a regular basis from now onwards. Okay, so for the pre-board one, we basically focus on your D and F block elements. It's already completed, and the organic part. After this chapter, I'm going to start with the aldehyde chapter, and after that, I will complete your amines chapter. So your organic part will be completed, and in the inshallah, in your next pre-board, we will complete your good portion. Okay, because this batch has basically started very late, so that's why we have not completed your more slips. Only three chapters are completed. Okay, Rimda, so please on from now onwards, please be regular in the class.
Okay, ma'am.
And if there is any doubt, let me know. Okay, just stop me and just tell me to repeat.
Yes,
So, okay, so dehydration of alcohol. Okay, basically we were doing the methods of preparation of ethers by dehydration of your alcohol. So your mechanism, let's understand this mechanism because when you see the previous year questions, so they just ask you the direct mechanism. They will give you this reaction, okay, in which the from alcohol is being converted to a ether, okay, and they will ask you the mechanism. What is the mechanism for this reaction? Okay, so that's why the mechanism is very important. So first step, this is the reaction CH3CH2OH. Ethanol, when you treat it with a strong acid, which is sulfuric acid, at this temperature, 414 Kelvin. Okay, you know very well at the high temperature, like if you use like 443 Kelvin temperature, then at this temperature, the alcohol will undergo elimination reaction. Instead of substitution, it will undergo elimination reaction and you will get a alkene. Okay, so you will not get a ether over here, you will get a alkene. So that's why we are using this temperature 414 Kelvin. So at 414 Kelvin and with the strong acid, this ethanol will get converted to a symmetrical ether. Symmetrical ether, right? So let's see. So protonation, first step is always the protonation of alcohol. So this is your alcohol, CH3, CH2OH. Okay, plus this H2SO4 give you the H plus ion, right? Now this oxygen of the ethanol, oxygen has a lone pair, right? So this oxygen, the lone pair will abstract this hydrogen. Okay, so basically it will protonate this. There will be a protonation of alcohol. So this oxygen lone pair, it will abstract this hydrogen, abstract this proton. And this structure you will write like this, CH3, this is CH2, okay. Then this is the oxygen, and oxygen has now 2 hydrogen, H and 1 H. Okay, now oxygen will get the positive charge because here the bond is now 3 bond, and oxygen can afford only 2 bond, right? So this is OH3. First step, protonation of alcohol. Now second step, the attack of nucleophile. The attack of nucleophile. Now let's see how the nucleophile will attack. Suppose this is your first CH3, CH2, OH. Now another, your CH3, CH2, OH, another mole, okay, another molecule of CH3, CH2, OH, ethanol, okay, and you will write this one, CH3, just a second, let me write it like this, CH3, CH2, and oxygen with 2 hydrogen. It has a positive charge. Okay. Now what happens over here? This is first molecule and this is the second molecule, right? This was the second molecule. इसका जो आपका protonation हुआ था, right? Protonation of alcohol, which was in the first step, and in the second step, this nucleophile will attack. Now, this oxygen, this will act as a nucleophile, right? This CH3, CH2, OH. So this OH will act as a nucleophile over here, and it attacks this carbon, right? Because this has a positive charge, and this will abstract this carbon, okay? And from here, the bond will, because this OH2, this is your H2O, right? H2O is quite unstable. So from here, the dehydration will occur. The dehydration will occur, and this oxygen, the lone pair of this oxygen will attack this carbon. So from here, water will be removed, minus H2O, right? And you will get 1, 2, 1, 2, and this oxygen, okay? And this oxygen has now 1 hydrogen also. Okay, now attach this one and okay, this oxygen, yeah, this attack this carbon, so you will write 1 and 2. 1 carbon, 2 carbon. And on this oxygen, there will be a positive charge. Is this a step clear? First and second, protonation of alcohol. Second step, attack of nucleophile. Is this clear?
Yes, ma'am.
Okay, so in the second step, you just got this one. Okay, so what is this? This is the ether, but here 1 hydrogen is there. So now what happens over there? Third step is the deprotonation. This proton will be removed. Okay, this proton will be removed, and so you will show like this. This has a positive charge, right? So this proton, okay, this bond will shift over here, and this proton will leave, and you will get ether, symmetrical ether. Plus this one is your H plus ion. Okay, again say this. This is your reaction, right? And these are the 3 steps. Okay, mechanism. First step, protonation of alcohol. Second step, attack of nucleophile. And the third step is deprotonation. Okay, please practice this numerical by your own after this class. Okay, so here's the remarks. It occurs via SN2 mechanism. What is SN2 mechanism? SN2 is a one-step mechanism. So see, the second step, the second step is the SN2, bimolecular your nucleophilic substitution reaction. Okay, what happens? This nucleophile will attack this carbon, right? And this group, this living group leave in a single step. Okay, that's why it is known as SN2 reaction, SN2 mechanism. SN2 mechanism occurs in a single step, the attack of nucleophile and the leaving of the living group. Okay, the living group leave the molecule in a single step. So that's why it is SN2 mechanism. This reaction occurs via SN2 mechanism. And in a SN2 mechanism, we know very well the rate of reaction will be, okay, the rate of reaction will be very fast in methanol, then primary, then secondary, then tertiary. In the tertiary alcohol, the rate of reaction is very slow. The rate of reaction is very slow. Why? Because in the tertiary alcohol, there are more plus I group, CH3OH. Okay, now you can see OH is attached to this carbon, and this carbon has three bulky group, three methyl group, which hinders, okay, which hinders the attack of nucleophile, which hinders the attack of nucleophile. So that's why in the tertiary alcohol, okay, the rate of reaction is very slow. After tertiary alcohol, in the secondary alcohol. So the secondary alcohol and tertiary alcohol give a significant amount of alkene with ether. Okay, so in these two, because of the hindrance, there will be a little bit elimination reaction also. There will be a little bit elimination reaction, and you know very well, if, elimination reaction results in a alkene formation. Okay, alkene is formed by a elimination reaction when something eliminate. Okay, so basically in the secondary and tertiary alcohol, what happens due to the presence of bulky group, okay, CH3 group, there will be a more hindrance, okay, there will be a more hindrance, and with the ether, with the formation of ether will be formed, but there will be a formation of alkene also, means you will get a mixture of alkene and ether when you take the secondary and tertiary alcohol. Why? The reason is because of the presence of more methyl group, which hinders the attack of nucleophile, which hinders the substitution reaction, right? So you will get a ether as well as alkene when you take the secondary as well as tertiary alcohol. Okay, so see this point. So therefore, this is not suitable for the preparation of symmetrical ethers using secondary and tertiary. Yeah, this one is very important, this point. So when you have to prepare the symmetrical ether, okay, symmetrical ether, so it is not suitable to take a secondary or tertiary alcohol. You always prefer the primary alcohol. When you have to prepare the symmetrical type of ether, so always prefer the primary alcohol. Is this clear?
Yes, ma'am.
Okay. So third point, this method of preparation is not suitable for the preparation of unsymmetrical ethers, because it would require two different alcohols and lead to the formation of mixture of ethers, which is difficult to separate out. Okay. Now you know very well what is unsymmetrical ether. So unsymmetrical ethers are those ethers in which there two different groups are attached to this ether linkage, oxygen linkage. Suppose we have here we have CH3 group, and here we have ethyl group, CH2 CH3 group. So what is this? This is both the groups are different. Okay, so this is an unsymmetrical type of ether. So this method of preparation means the dehydration of alcohol is not a suitable method for the preparation of unsymmetrical ether. Why? Because it will require two different alcohols. And when you take two different alcohols, so it will lead to a formation of mixture of ethers. You will not get a single ether. You will not get a single ether when you take the different alcohols. You will get a mixture of ethers, and the mixture of ethers is very difficult to separate, because if you require only one type of ether, okay, if you are preparing only one type of ether and if you are getting mixtures of ether, so how you will separate it out? It will take time. Okay, so to purify the mixture, to separate the mixtures, so that's why this method is not suitable for the preparation of unsymmetrical ether. This method is suitable for the symmetrical type of ether preparation, and for the symmetrical type of ether preparation you are required a primary alcohol. Always take the primary alcohol. Always prefer the primary alcohol. Okay. Secondary and tertiary alcohol will hinders the nucleophilic substitution reaction, and it will form a little bit amount of alkene also. Elimination reaction will also occur over here, and you will get a mixture of your ether plus your alkene when you take the secondary and tertiary ether, tertiary alcohol, right? Okay, so suppose we have this. This is a unsymmetrical type of ether. Okay, and if we have to prepare this unsymmetrical type of ether using the dehydration of alcohol. Okay, we just have to treat it with sulfuric acid with at 414 Kelvin temperature. So what you will get? So see, This will require, you can see this is an unsymmetrical type of ether. So this will require two different alcohol. One alcohol must have two carbon, means ethanol, and one alcohol with one carbon, which is your methanol. When methanol and ethanol reacts together, undergo dehydration reaction in the presence of sulfuric acid. Okay, let's see, suppose we have a 1,2 carbon. So this is oxygen linkage, right? This is the ether linkage. So when 1,2 carbon, this is a ethyl and this is methyl. Okay, so ethyl say just prepare the alcohol, ethanol plus what is this? Methyl. So methyl, just attach the OH group. So these two alcohols when react together in the presence of sulfuric acid at 414 Kelvin. Okay, so what is this? This is a dehydration reaction, dehydration of alcohol. So it will undergo the substitution reaction, and here you will not get a single ether, you will get a mixtures of ether. So first thing you will get a 1, 2, this is your, so you will get a, what you're supposed to do, just remove this hydrogen, right? In the dehydration reaction, as I have discussed in the previous class, just remove this hydrogen and attach this group. Okay, this group. So this, as it is, remove this hydrogen and again attach this group. So you are just getting the diethyl ether, right? Diethyl ether. Okay, now next product you will get this from this one. So just remove this hydrogen. It will give you CH3 oxygen. Okay, and again repeat this CH3. So this is you will get a dimethyl ether. Dimethyl ether. Plus here it will not give you only two products. It will give you three products. So after this you will get a mixture of these two ether. One here, this ethyl oxygen linkage and this CH3 will attach to it. So you will get a unsymmetrical, two symmetrical ether and one unsymmetrical ether you will get. Okay, so that's why this method of preparation is not suitable for the preparation of unsymmetrical ether, because you are just getting the undesired product, unsymmetrical ether. But these two are not the desired one. Okay, but these two are not the desired one. You don't need these two products. Okay, but you are getting the mixtures of these three ethers when you are just trying to prepare this dye. This is your ethyl methyl ether. Okay, if you are preparing the ethyl methyl ether, but you are not getting only ethyl methyl ether, you are just getting the diethyl ether as well as the dimethyl ether. Okay, so at last you have to separate them out to get this. To get this, you have to separate all the three. So that's why this method of preparation is not suitable for the preparation of unsymmetrical type of ether. This is suitable only for the symmetrical type of dehydration of alcohol process. Clear to everyone? Ali and Rimda?
No.
Okay. Yeah, this is the question. Question is, can you explain why bimolecular dehydration is not appropriate for the preparation of ethyl methyl ether? Right? Why it is not prepared? It is appropriate. So this point you can write. Okay, you can write the answer, this 3 point with this example. This is the example of your ethyl methyl ether. Okay, just if this question come in your exam, just write on this point, third point, and just give this reaction. Okay, the preparative method of your ethyl methyl ether. Because in this reaction, you are just getting the mixtures of your symmetrical ether plus your unsymmetrical ether. And at last, you have to separate them out. So that's why this is not preferred method. Okay. Next is your from alkyl halide. From alkyl halide, how we can prepare the ether. And this process is known as Williamson ether synthesis. The name reaction, again important reaction, right? So how from alkyl halides, how we can prepare the ether. So when haloalkanes is treated with suitable sodium alkoxide. Sodium alkoxide. This is the sodium alkoxide, RONA. Sodium And what is this? RO is your alkoxide. Oxide with R means alkyl group. So this is alkoxide, sodium alkoxide group. So when haloalkene, okay, is treated with suitable sodium alkoxide, SN2 reaction takes place. Again, bimolecular nucleophilic substitution reaction takes place, which forms a corresponding ether. Which forms a corresponding ether. Okay. Sorry. So this is the reaction. ROH. Now the question is how you will prepare the sodium alkoxide. So first let's see how we can prepare the sodium alkoxide. When the alcohol is treated with sodium metal, so you will get sodium alkoxide plus H2 gas. H2 gas will be liberated out and you will get a RONA, sodium alkoxide. Now in the second step, the sodium alkoxide plus your RX, haloalkene. Okay, so we are just doing the Williamson ether synthesis. When haloalkane is treated with your sodium alkoxide, what you are supposed to, this oxygen has a lone pair. This oxygen has a lone pair. And between this R and X, which one is more electronegative? X is more electronegative, right? So X will acquire partial negative charge and this R group will acquire partial positive charge. So this lone pair of this oxygen will attack this R group, right? This lone pair of this oxygen will attack this R group. Why? Because it is partial positive. Okay, when it attacks this group, so you will get ROR dash. Suppose this is your R dash, R dash X. So you will get ROR dash and NX will be removed. NX will be removed. So that's what you are supposed to do. That's very simple. This oxygen. Okay, this is again a SN2 reaction, right? So only one step mechanism will be done. So the attack of nucleophile, okay, so what is nucleophile over here? This RONA, right? RO minus. So this oxygen lone pair will attack this R group, okay, and this Na will be removed with X. It will get combined with X and it will form Na, sodium salt basically, okay, and you will get ROR dash, ROR dash, which is your ether, which is your ether. Is this clear? And this process is known as Williamson ether synthesis. Clear or not?
No.
Okay. Okay. So, one question, I will do it for you, and I will give you some questions too, which you will solve. Suppose this is your alcohol, right? So first step is when alcohol is treated with sodium, right? So when alcohol is treated with sodium in the first step, so you will get what you are supposed to do. This hydrogen will be replaced by this Na and you will get 1,2 carbon ONA, okay, alkoxide. Your sodium alkoxide, sodium ethoxide you will get plus H2. No need to write on the H2. Okay, just byproduct, no need to write. Next step, when you treat the sodium alkoxide with CH3Br, which is your haloalkene, right? So this bromine will get a partial negative charge and the C carbon of the methyl group will get the partial positive charge. So this oxygen, the lone pair of the oxygen will attack this alkyl group, okay? And this sodium will get combined with bromine and it will form NaBr as a byproduct. And you will get 1,2 carbon with oxygen and this CH3 group. Is this a step clear? First
No.
step. Okay, first step is alcohol. Just treat the alcohol with a sodium metal. You will get a alkoxide, sodium alkoxide. This hydrogen will be replaced by the sodium. Okay, just remove this hydrogen and attach the sodium over here. You will get the sodium alkoxide. Second step, when you treat the sodium alkoxide with CH3Br, what is this? Haloalkane. And this reaction is known as Williamson ether synthesis. So this CH3 and Br, so between this carbon and bromine is more electronegative, so it will acquire partial negative charge. So this carbon will acquire partial positive charge. So this negative oxygen is oxygen lone pair. Lone pair is negative electron. Again, it's an electron negatively charged, so it will attack this carbon. which is positive, right? And the sodium will get combined with bromine and NaBr will be formed, right? So 1, 2 carbon, oxygen, and the CH. This is your ether. That's how ether is prepared using the Williamson ether synthesis. Okay, now do this question quickly. Question number 2, 3, 4, 5. Sometimes they will directly give you the sodium alkoxide, and sometimes they will give you the alcohol when it is treated with the sodium. Quickly solve this question. Yes, done. Yes, Ali, tell me the first answer.
CH3, CH2, O, CH2, CH2 plus NAPR.
Okay. Okay, very good. Yes, Rimda, tell me the third one.
CH3, CHO, CH2, CH3 plus NaCl.
CH3, CH2, then CH3,
CHO.
CHO. Okay, see this structure. I'm not getting your point. So see this. What is this? This is your alkoxide. Okay, so alkoxide is the nucleophile over here, right? Because this oxygen of this alkoxide will attack this carbon. It will attack this carbon, and from here, this chlorine will remove. Okay, this chlorine will be removed. So it will form. Okay. So Na, this sodium and this chlorine will get combined and they will form NaCl, right? And 1, 2, 3 carbons. First write it down. This 1, 2, 3 carbon. Then this oxygen, and it's combining with this 2 carbon, right? 1 and 2 carbon. So you will write like this. Right? This is your compound. CH3, CH2, okay, then CH3 and here oxygen with C2H5, ethyl. Is your answer correct, Rimda?
Yes, ma'am.
Okay, so follow the same mechanism, you will get the proper answer. Yes, fourth one, Ali, tell me the answer.
C6H5, O, CH3 plus NAPR.
Okay. O, CH3 plus NaPr, good. This oxygen will attack this carbon, and from here the bromine will leave, and it will get combined with sodium, form sodium bromine, NaPr. Okay, so this cyclopentane ring with oxygen and CH3 group over here. Yes, the last one, Rimda. Yes, Rimda, explain the product.
Ma'am, C6H11 OCH2CH3 plus NaBr.
Okay, very good. O, C2, CH2, CH3 plus Na. Yeah, so that is the Williamson ether synthesis. Okay, so you know very well what is the rate of reactivity, right? The reactivity rate of SN2 reaction, because it's again the Williamson ether synthesis is again by the SN2 mechanism. Okay, the reaction occurs via your SN2 mechanism. So the order of reactivity will be the primary, then your secondary, then your tertiary. Primary alkyl halide, secondary alkyl halide, and the tertiary alkyl halide. Okay. So remarks Williamson, and yeah, what is nucleophile over here? So nucleophile is the alkoxide. Okay, there's this alkoxide, this ONA. This is your uh, nucleophile over here, right? So this oxygen, because this oxygen lone pair is acting over here. It's attacking on this carbon, so that's why it is a nucleophile. So Williamson ether synthesis is an SN2 reaction where alkoxide is your nucleophile and the RX is your substrate. What is substrate over here? In the nucleophilic substitution reaction, one is your substrate, okay, and the other one is your nucleophile. So nucleophile over here is alkoxide and the substrate is your RX. So this nucleophile attack the substrate. Okay, that's our alkyl group of this substrate, and you will get the product. Okay. So haloalkane should be less hindered. You should be very careful in this reaction mechanism. The haloalkane should be less hindered. Means you will prefer primary haloalkane. You will always take primary haloalkane because primary haloalkane has less alkyl group than your secondary and tertiary. Okay, means primary alkyl halide is less hindered. So that's why the preferred alkyl halide you will take is primary one. To form the unsymmetrical ether, always remember, to form the unsymmetrical ether, primary alkyl halide should be used preferably. Okay, so if you use a secondary and tertiary alkyl halide, it leads to the formation of alkene with the ether. Okay, it will give you alkene plus ether. Okay, and I have explained it to you why. Because in the secondary and tertiary haloalkene, there are more alkyl group, and alkyl group are plus side group, right? So they will hinder the attack of nucleophile. Okay, so instead of substitution reaction, elimination will occur. Okay, and you will get, there will be a formation of alkene. Why? Because they are more hindered. Secondary and tertiary haloalkane are more hindered. So that's why primary alkyl halide should be preferred. What should be preferred? Primary alkyl halide. Okay, so let's see. This is your example. Suppose this is the, what is this? This is an unsymmetrical type of your ether, unsymmetrical ether. Okay, so you can see this is oxygen linkage. There is one group which is ethyl group, and there is another group, okay, which is your tertiary group, right? 1, 2, 3 carbon chain. Okay, so this group and this group both are different, so this is unsymmetrical type. Now the question is because if you do the Williamson ether synthesis, how you will prepare this product using the Williamson ether synthesis? So you know very well, for the Williamson ether synthesis there should be two particles, two compounds should be there, sodium alkoxide. Okay, first you have to prepare the alkoxide, and the second one is your haloalkane. Okay, because Williamson ether synthesis is when the haloalkane is treated with the sodium alkoxide, so it will give you a corresponding ether, right? So now you have to choose. Suppose this is your product, and from the product, okay, from the product, you have been asked to write down the reaction Williamson ether synthesis, how you will prepare this product using the Williamson ether synthesis. Okay, now first step, you will analyze the question, analyze the product, right? And this is your ethyl group. Okay, what is this? This is a primary. This is a primary structure, and this is your, what is this? This is a secondary structure. This is your, this carbon is your secondary carbon, right? Because two groups are attached to this carbon. And this carbon is your primary because only one carbon, one group is attached. First, you will check whether there is a which group is primary and which group is secondary. Now you will prefer primary alkyl halide. Primary alkyl halide, right? So this primary structure, it will form a alkyl halide, right? This two. 1 2 carbon से आप क्या बनाओगे alkyl halide. So 1 2 carbon, just attach any halogen group. Okay, bromine, chlorine, anything, just attach this. So I'm just attaching the bromine, so it will form, what is this? This is the alkyl halide. Okay, alkyl halide, you just got the alkyl halide. Now the second component क्या चाहिए आपको? Alkoxide. So what is alkoxide? ONA, RONA, right? So this is your R group. R group is the secondary group, and this is the O group. What you are supposed to do? Na. So basically the bond will break from here. Okay, this is a primary one, so primary structure से primary group से आप क्या बनाओगे? Haloalkene. And the remaining fragment will form the alkoxide. The remaining fragment will form the alkoxide, means this fragment 1 2 oxygen, right? And from this oxygen just attach the sodium, so this will form a sodium alkoxide. These are the two reactants. So from product, if there is a product given in your exam, they will give you the product and they will ask you what will be the how you will write on the Williamson ether synthesis using this. From Williamson ether synthesis, how you will form this product. Okay. So you first thing, you have to analyze the question. Just check it out whether which group is primary and which group is secondary, right? So the primary, you will prefer the primary group, your primary group, to form the alkyl halide. Primary alkyl halide आपको form करना है, right? This primary group से. So this will form this from this carbon, this two carbon chain. You will prepare the your any bromide, your chloride, anything. Okay, any halogen group you have to attach. and the remaining fragment will form the alkoxide, sodium alkoxide. So just attach the Na to this oxygen and you will get this. So these are the two groups. These are the two reactants. Now, how you will write on the reaction? Just do the same thing. This oxygen, what is this? This is again a nucleophilic SN2 reaction आपको कराना है, right? And SN2 is a one-step mechanism, one-step reaction. So what is this? This is a nucleophile. Alkoxide is the nucleophile and the haloalkene is your substrate. Right, so this nucleophile, this oxygen or the lone pair of this oxygen will attack which carbon? This carbon to which the bromine is attached. Right, and this bromine is a good living group, so just it leave. Okay, and it will combine with sodium and it will form NaBr as a byproduct. And what about this? This is structure. This oxygen, okay, and oxygen में क्या attach करना है? This carbon and this group. So CH2, CH3, CH2 and CH3. This is form. You can check over here. This is the product. Yeah, this is the product. It means our reactants are correct. Getting my point? Is this clear? Is this concept clear, Imdhan Ali? How you will choose the alkyl halide and how you will choose alkoxide, which groups? Okay, so if it is clear, then let's do some questions. Okay. Suppose this is an alkoxybenzene. What is this? Alkoxybenzene. Benzene, okay. And what is this? Alkoxy group is attached to the benzene. RO group. Alkyl group with oxygen. What is this? This is alkoxy. Alkoxy. Alkyl plus oxygen linkage, alkoxy. When alkoxy group is attached to the benzene, okay, so how you will break the bond? Which bond will be cleaved and which group you will which group will be formed as a alkoxide and which group will be formed as a alkyl, your halogen alkyl, your haloalkene basically, right? So now see here, there are two cases. For the alkoxybenzene, if alkoxybenzene is given, okay, as a product, as the ether, you can see this is a ether linkage, oxygen linkage. Here it is a alkyl group and here it is a benzyl. Okay, your benzene ring, aryl group. Benzene ring and here it is a alkyl group. Now the question is which bond you will cleave, this or this? Which bond you will cleave, this bond or this bond? And from which group? From which group? From alkyl group or from the aryl group? You will prepare the alkoxide. Okay, so see, there are two conditions. First, you can break this bond or you can break this bond. So first, I'm just breaking this bond. Okay, when I break this bond, so R will form the halogen, right? R, Br. When I break this bond, so it will form R and Br. Okay, your haloalkene, your alkyl bromide. Okay, and this oxygen में क्या आप attach करोगे? Na. O, Na. Okay, so this will form your sodium aryl oxide. What is this? Aryl oxide or phenoxide. Okay, sodium phenoxide. First case. Now the second case is when you break this bond. Okay, this benzene ring hai and yahan pe this bond if you break. Now the question is, can we break this bond? Is it possible to break this bond, oxygen and this benzene ring bond, this carbon bond? So no. Why? Because this oxygen, okay, the lone pair of oxygen of this oxygen is involved in the resonance with this benzene ring. And due to the resonance, there is a partial double bond character between this carbon and oxygen. So that's why to break this bond, this bond can't be break. Why? Due to the presence of double bond, which is very difficult to break. So that's why if you break this, अगर आप ये break कर सकते हो, so there will be a formation of your this one. Okay, your aryl halogen with aryl group. Okay, halogen with aryl group. But plus this will, when you break this bond, so you will get RO. Okay, so Na will get attached to this oxygen. RONA. Now the question is this path, there are two paths, path A and path B. Which path is correct and which one is wrong? So this A path is correct. Why it is correct? Because when you just remove, when you break this bond, so the R group, okay, R group, alkyl group will form the your your haloalkane. Alkyl, this alkyl group will form the haloalkane, and this group O, benzene with oxygen linkage, this will form the phenoxide ion. This will be sodium phenoxide and haloalkane. Okay, so by the reaction of phenoxide, sodium phenoxide and haloalkane, we can prepare the alkoxybenzene. But we can't prepare the reaction of this RONA or your sodium alkoxide with your aryl halide. Okay, this aryl halide. Why? Because this halogen, suppose this is a halogen, if you attach the halogen, so halogen is an electron donating group. It just donate the electron to the benzene ring, and due to the resonance, this is involved in the resonance with the benzene ring, right? And due to the resonance, there is a double bond character between the carbon, this carbon of the benzene and the halogen, and which is very difficult to break, and there will be, so the nucleophilic substitution reaction will be very difficult for the your aryl halide. Okay, you know very well aryl halide don't undergo nucleophilic substitution reaction, right? Only under drastic condition, like in dose process, जो हमने पढ़ा था, dose process में we can do the nucleophilic substitution reaction at very harsh condition, very high temperature and pressure के under. Okay, so at normal temperature, at normal conditions, a nucleophilic substitution reaction of aryl halide is not possible. So, and this is your aryl halide. And why this is so? Due to the formation of double bond between this carbon and your halogen. Okay, partial double bond character between the carbon and this halogen. So this route is not possible. This route is not possible, right? So always you don't break this bond. Okay, if this is a ether, so always break this oxygen. After this oxygen, just break this bond, not this bond, because this has a partial double bond character, which is very difficult to break. Is this clear?
Ma'am.
Okay, so here you can write alkoxybenzene cannot be prepared using haloarene. Okay, alkoxybenzene cannot be prepared using haloarenes. Why? Because haloarenes don't show nucleophilic substitution reaction. Therefore, alkoxybenzene are prepared using phenoxide and haloalkene. Okay, now let's see the question. Question is, write the names of reagents and equations for the preparation of the following ethers by Williamson synthesis. Right. So we have to write down the names of reagents and equations for the Williamson synthesis. So always remember, for the Williamson synthesis, we need two components. Alkoxide, sodium alkoxide plus your haloalkene, right? So first question. These are the products which is given. One, propoxypropane. How you will draw the structure of this one? Propoxypropane. 1, 2, 3. 3 carbon chain means propoxy, and 1, 2, 3. This is your propoxypropane. Okay. Second, ethoxybenzene. Benzene. This is it. 1, 2 carbon with oxygen, ethoxybenzene. Okay, let's do first two first. Yeah. So how you will, okay, you will have to write down the names of reactants, reagents, and equations for the preparation of the following. Okay, so for the Williamson synthesis, two things are needed. Alkoxide plus your haloalkane. So here, this is a symmetrical type of ether, right? So you can break any bond. Okay, so you have to break this. This is oxygen linkage, right? So you have to break either this bond or this bond. because both are the symmetrical one. So no need to check it out which one is primary, which one is secondary. Both are primary and both are same structure, propane, propane. Okay, so you can break any bond. So I'm just breaking this bond. Okay, just break this bond, and from this bond, 1, 2, 3 carbon, this group, you can prepare the haloalkane, right? So 1, 2, 3 carbon, 1, 2, 3 carbon, and attach the bromine. 1, 2, 3, 1, 2, 1, 2, 3, and here bromine, right? Plus the remaining fragment, this fragment, 1, 2, 3 carbon with oxygen. Just attach the sodium over here. It will form the sodium alkoxide. Okay, so these are the reagents for this product. Now write on the equation. We have to write on the equations also. So equation will become this oxygen, right? It is a nucleophile over here, so it will attack this carbon, and this bromine will leave, and it will form 1, 2, 1, 2, 3. This oxygen, then 1, 2, 3, 2, 3. Right, so this product. This is the product, final product. Okay, is this question clear, Ali and Rinda?
No.
Yes.
Okay, if it is clear, then do the rest. Ethoxybenzene, 2-methoxy 2-methylpropane, and 1-methoxyethane. Okay, always remember, see the second one. Second is your ethoxybenzene. Okay, so as I told you, you don't break this bond. Okay, this benzene, don't break this bond. Why? Because this is involved in the resonance with this oxygen, right? Oxygen, lone pair is involved in the resonance with the benzene ring, and there is a partial double bond character. So ये break नहीं होगा ये bond. Okay, so you have to break this bond. Okay, now quickly do the rest of the question. Ethoxybenzene, 2-methoxy 2-methylpropane, and the last one, 1-methoxyethane. Yes, done. Yes, Ali, tell me this one. What are the reagents for that? Second question. Yes, Ali, what is the reagent in the second question?
Sodium phenoxide and CH3CH2.
Ambia.
CH3CH2
Right?
Cl per pm.
Yes. And your final product will be?
C6H5OCH3
Yeah.
CH2 NaCl.
Okay. Okay, so the next question is 2-methoxy, 2-methylpropane. Right, so propane, just draw the structure of propane, 1, 2, 3 carbon. 1, 2, 3 carbon chain. And on the second position, there is a methoxy, means OCH3, OCH3. And on the second position, there is a methyl group 2. One methyl group and one methoxy group, this one. So this is the structure. How you will break this structure? And the fourth structure is 1-methoxyethane. I think we have discussed this. 1-methoxyethane. Yes. Third question, Rimda. What are the reagent for that? Here it is. This question is, see, oxygen. What you are supposed to do, just see the oxygen linkage, where the oxygen linkage is present. Okay, and just uh, just object the group. This oxygen linkage, right? There are two groups. One is methyl group and the other is this whole thing, right? So which bond you will break? So this is your primary, this carbon, right? This methyl group, but this is your tertiary, right? This is your tertiary group. So from which group you will make the haloalkene? So again, I just told you haloalkene किससे आप बनाओगे? Primary structure. Okay, always prefer the primary structure to form the haloalkene. So this methyl group, right? So this is a structure, right? It's the CH3 only, and this is quite branching. There is quite branching over here, right? So this carbon is tertiary carbon, right? So this tertiary carbon will form the alkoxide, and the CH3 you will prefer the primary group or primary carbon or this hydrocarbon chain to prepare the haloalkene, right? Primary haloalkene are preferred in this reaction. CH3 से आप क्या prepare करोगे? The CH3Br and the remaining. Okay, so basically you just break this bond. CH3, this oxygen, and this bond you break. So this remaining thing will form the alkoxide. Means you will attach the Na to this oxygen and you will write this. Okay, 2-methyl. Okay, 2-methyl, and two position where there is a sodium with oxygen. This is your methoxy. This is your alkoxide. Okay, and this is your CH3Br haloalkene. Okay, so basically this oxygen, okay, the lone pair of the oxygen just attack this carbon and this bromine will leave and you will get CH3, this is CH, and here O and the CH3. This is your final product. Okay, is this question clear? Okay, see the fourth one. Fourth one we have already discussed that. This is your ethyl methyl ether, right? Ethyl methyl ether. This is the first, this is the second, right? First group, second group. This is the oxygen linkage. Now, This methyl group CH3, only one number of carbon and here two number of carbon. So always remember, okay, suppose if both are primary structure, right? So as I told you, the haloalkane should be less hindered. It should be less hindered. So which group? First group or second group? Which one is less hindered? CH3 is less hindered, right? Because in first structure, it's a methyl group. So if this carbon CH2 has one CH3 group, right? One more bulky group. So there will be a more hindrance as compared to the CH3. Right, so CH3, methyl is less hindered as compared to the ethyl group. So that's why you will prefer the methyl group to prepare the haloalkene. So you will prepare methyl bromide CH3Br and the remaining group, this group will form the alkoxide CH3, CH2, oxygen and then Na. And what is the final product? This oxygen, lone pair of this oxygen will attack this carbon and bromine will leave. So you will get O and CH3. That is your product. Okay. Okay, see the next question. Ditert, Ditertiary butyl ether. What is this? This is your ether linkage. And what is this? This is your carbon, tertiary carbon. This carbon is tertiary carbon. And what is this structure? Tertiary butyl. Tertiary butyl. And both the sides, it's a symmetrical structure. Both the sides, same group is attached. So that's why it is ditert butyl ether. So ditert butyl ether cannot be prepared by Williamson ether synthesis. Why? What is the reason behind that? Why butyl ether cannot be prepared by Williamson ether synthesis? Okay, now you can see. So as I explained it to you, we prefer the primary haloalkane. Primary haloalkane in the Williamson ether synthesis because primary haloalkane are less hindered. Primary haloalkane are less hindered, so that's why we prefer that. But here you can see both groups are oxygen linkage is there, right? Both the groups are tertiary one. This is again tertiary, this is again tertiary. Okay, and if you take the tertiary haloalkane, so there will be more hindrance. Okay, there will be more hindrance, and due to that, it will form the alkene. Okay, it will give you a mixture of alkene plus your ether. Okay, so that's why ditert butyl ether cannot be prepared by Williamson ether synthesis because there will be more hindrance. Because this, if you have to prepare the ditertiary butyl ether, so you have no option. You will require for this, you will break this bond, either this bond or this bond. So for that it will be CH3, you will attach this carbon. इस carbon पे आप क्या attach करोगे? Bromine. And to this oxygen you will attach sodium, right? So this will form your tertiary, okay, tertiary sodium oxide, okay, sodium alkoxide, tertiary alkoxide plus your tertiary haloalkane as well, right? So this required a reaction of tertiary haloalkenes with tertiary alkoxide, which results in the formation of alkene. So instead of substitution reaction, nucleophilic substitution reaction, elimination reaction will occur, and due to the elimination reaction, you will get a alkene. You will get a alkene due to the steric hindrance, due to the more bulky group present in this, right? CH3, CH3, CH3. Okay, CH3, 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 right? So there is more CH3 group, and due to that, there will be more hindrance. And due to the more hindrance, sorry, it will form a alkene instead of your ester. So that's why ditert butyl ether cannot be prepared by Williamson ether synthesis. Is this clear? What is the reason behind that? Yes, Ali and Rinda, is this clear, Bacho? Any doubts from this? Okay. Okay, I will provide the notes after this class. So no need to make the notes here. Okay, now tell me, this group. Suppose we have diphenyl ether. This is your diphenyl ether, right? Oxygen linkage and both the sides aryl group is attached. Okay, benzene ring attached. So now tell me, can we do the Williamson ether synthesis for this reaction to make this product? Can we use the Williamson ether synthesis for the formation of diphenyl ether? So no. Why? Why it is no? Because you can see this is oxygen linkage, this is a benzene ring, and this is again a benzene ring. So this oxygen lone pair is involved in the resonance with both the benzene ring. So there will be a partial double bond character, okay, between both the carbon of both the benzene ring with the oxygen. So that's why this will require a reaction of phenoxide with the haloarine. Okay, but you know very well haloarenes don't show nucleophilic substitution reaction. Okay, how this will be formed? If you want to prepare this diphenyl ether by using the Williamson ether synthesis. So you have to prepare it using alkoxide. One should be alkoxide and one should be the haloarine, right? Because both the groups are alkene, arene over here. Okay, aryl group. Okay, aromatic system. So you can break this bond or this bond, but both the bonds are involved in the resonance, and due to that, there is a partial double bond character which is very difficult to break. Okay, and also the haloarenes don't show the nucleophilic substitution reaction. So due to the partial double bond character between the carbon and our X, okay, this carbon and this oxygen भी आप कह सकते हो, and if you break this bond, anyhow, if you break this bond, so there will be a Na plus your phenoxide ion plus your haloarenes. Okay, and this haloarenes, this carbon and a halogen between this, so there will be a partial double bond character, okay, which is very difficult to break. Okay, so that's the reason. You can write down this reason. This requires reaction of phenoxide ion, okay, phenoxide ion with the haloarenes. But haloarenes don't show nucleophilic substitution reaction. Why? Due to the partial double bond character of CX, the CX. Okay, clear this point? This can be asked in the statement type of question. Okay. Okay, next see the physical properties of ether. Physical properties of ether. So ethers are slightly polar. Ethers कैसे होते हैं? They are slightly polar. And ethers have lower boiling point than alcohol. Why? Due to the absence of hydrogen bond in ether. Okay, due to the absence of, because hydrogen bond के लिए क्या requirement होती है? Hydrogen should be attached to most electronegative element just like your fluorine, oxygen or nitrogen. For the hydrogen bond, what is the requirement? The hydrogen should be attached to either nitrogen, oxygen or fluorine, means the most electronegative element. Then only it can form the hydrogen bond, right? So this is slightly polar, and ethers have lower boiling point than alcohol, right? Because alcohol have hydrogen bonding, right? But ethers lacks hydrogen bonding. And due to the absence of hydrogen bonding in ethers, the boiling point is low as compared to the alcohol. Third point is boiling point of ethers is slightly higher than the hydrocarbon. सिंपल हाइड्रोकार्बन चेन से अगर आप कंपेयर करोगे तो boiling point of ethers is slightly higher. Okay, with the same molar mass. If both ether and the hydrocarbon, okay, is having a same molar mass, both have same molar mass, then you can compare between these two, and the boiling point of ether is slightly higher than the hydrocarbon chain with the same molar mass. Next point is when you try to dilute the ether in a water, right? So ethers are soluble in water. Why? Because they are slightly polar. They are slightly polar, so they are soluble in water as they can form hydrogen bond with water. They can form a hydrogen. They can't. They have not a hydrogen bonding in itself, but they can form a hydrogen bond with water. See how? So this is your water, H2O, right? H2O. And this hydrogen in water, hydrogen is attached to this oxygen, electronegative element, right? So it can form the hydrogen bonding. And this ether, ROR group, ROR group, ether. So the lone pair of this oxygen, lone pair of this oxygen, it will make bond with this hydrogen, hydrogen of this water, right? So it makes the hydrogen bond with water. So that's why ethers are soluble in water. Why? Because they can form hydrogen bond with water. Water के साथ ये hydrogen bond बना लेते हैं. Due to that, they are soluble in water. Are you getting my point? Okay, see the next one. Increase in the number of carbon atoms will decrease the solubility. If you increase the number of carbon atoms, then the solubility will decrease. Okay, so a carbon atom has a inverse relationship between the solubility. If you increase the number of carbon atoms, then the solubility will decrease and vice versa. Okay, because the number of carbon or the number of alkyl group, more the bulky alkyl group, it will hinders the solubility. It will hinders the formation of hydrogen bonding, basically. It just hinders the formation of hydrogen bonding, and uh, um, due to the formation, not formation of the hydrogen bonding, the solubility will decrease. So that's why the number of carbon atom is inversely proportional to the solubility. Okay, so that's all about the physical properties of ether. Next is your chemical properties of ether. Chemical properties of ether. Okay, now see. So chemical properties. So first reaction we will see in which we will cleave the CO bond, the carbon and oxygen bond in ether. We will just cleave, we will just break this bond. So when the carbon and oxygen bond is cleaved, so here we will study about the reaction with HX. Reaction with the HX. Okay, halo acids. Okay, halogen acids. So treatment of ethers with HX leads to the formation of corresponding alcohol and haloalkene. So when you treat the ether with the halo acid, HX के साथ अगर आप treat कराते हो, any HX, right? Halo acids. So it will lead to the formation of alcohol plus your haloalkene. Now see what you are supposed to do. What you are supposed to do. This oxygen has a lone pair, right? So, and this hydrogen is H, when it dissociates, so it will get positive charge and this will get negative charge because the halogen are electronegative, right? So this hydrogen, okay, this oxygen will abstract this hydrogen and this bond will break. And this bond will break. When this bond will break, this R alkyl group will get attached to this X. This will get attached to the X and it will form RX. RX, which it means haloalkene. It will form haloalkane and it will form RO and this hydrogen means alcohol. So in this question, what you are supposed to do, you have to break carbon and oxygen bond. This alkyl, okay, alkyl group has a carbon. So carbon and oxygen bond just cleaved, and just this H plus will get attached to this oxygen and X will get attached to this alkyl group. That's it. So first, symmetrical ether. When you take the symmetrical ether and when you treat it with the halogen acid HX, okay, HI के साथ यहाँ पे अगर treat कराते हो, okay, iodide, hydrogen iodide. So this is a symmetrical ether. So if you're having a symmetrical ether, so don't worry over here. Okay, no need to worry about that. So which bond you will cleave? If it is this is oxygen linkage, right? This is CH3, CH3. Both groups are same. Okay, now question is because it's a cleavage of CO bond. What you're supposed to do, just you have to cleave the CO bond. Okay, so which CO bond you will break? So it is up to you. It's a symmetrical ether, so you can break any CO bond. So I'm just breaking one CO bond, right? This H plus, okay, this oxygen will get the H plus, and this CH3 will get the I. So, and it will form, this is I, sorry, and it will form CH3OH plus your CH3I. CH3I. So it will form methyl alcohol plus methyl iodide. Is it clear what you are supposed to do here? Yes, Ali and Rimda?
Yes, ma'am.
Yeah, so just break this oxygen carbon bond. Okay, this H plus, this positive part of the halogen acid will get attached to the negative part, which is oxygen. And this negative part of the halogen acid means iodine or the halogen will get attached to the carbon. Okay, this positive one. And you will get two products, alcohol plus your alkyl halide. Do the second and third question. Yes, Ali. Yes, Rimda, you tell me the second one. What will be the product here?
CH2 CH3 Br plus CH3 CH2H.
Yes, very good. So you will get a ethyl alcohol plus ethyl bromide. Yes, Ali, the last one.
CH3, CH2, CH2OH plus CH3, CH2, CH2I.
Basically, you will get a isopropyl. What is this? Isostructure. Isopropyl alcohol plus your isopropyl iodide or bromide. Sorry, you will get a iodide. HI है ना यहाँ पे, so you will attach iodine. Okay. Isopropyl alcohol plus your isopropyl iodide. This is for the symmetrical one. For the symmetrical one, it's very simple. But for the unsymmetrical one, you have to be very careful. Okay. So for the if there is an unsymmetrical type of ether, right? So what you're supposed to do. So first, suppose this is a question. First question, see this. So this is oxygen linkage. There is one group, another group. Now the question is which CO bond you will cleave? Which CO bond you will cleave? Okay, because at last you will get a alcohol plus your alkyl halide. Alcohol plus your alkyl halide. So first see, you have to check whether there is a tertiary alpha carbon present or not. Check, first step, check if there is any tertiary alpha carbon. So this is oxygen linkage, right? So this is one carbon, alpha carbon, suppose alpha 1, and this is your alpha 2. Now check it whether tertiary alpha carbon is present or not. So yes, this is tertiary alpha carbon. This alpha carbon is tertiary. This is tertiary, right? This carbon has further 3 groups. Okay, 3 groups are attached to this carbon. So this is a tertiary alpha carbon, and this alpha carbon is your primary one. That's the first thing. Second thing is, if you have analyzed which one is your tertiary carbon, then attach the halogen atom to that carbon. Attach the halogen atom to this carbon, right? Bromine is the halogen atom. Just attach and break this bond. Just attach the halogen atom to the tertiary carbon, right? And break this bond, and this remaining fragment will form the alcohol. Okay, remaining fragment will form the alcohol. So you will get here bromine plus this one. Yeah. Here you will get the tertiary haloalkane. But in the Williamson ether synthesis, you should be very careful. You will prefer only the primary alcohol because it occurs via a nucleophilic substitution reaction, right? And in the nucleophilic substitution reaction, primary alcohol or primary haloalkane is less hindered. So you have to choose the less hindered haloalkane. But here you will take first you have to analyze which one is your tertiary alpha carbon and just attach the halogen, which one is given in your reagent part. Suppose it is HPr, so just attach the bromine to the tertiary alpha carbon. Suppose it's a HI, so attach the iodine to the alpha position. Tertiary, which is having a tertiary alpha carbon. Is this clear?
Yes, ma'am.
Okay, then do the second one. Analyze this structure. After that, check it whether there is a tertiary alpha carbon or not. If there is a tertiary alpha carbon, just attach the halogen atom to that carbon and break the adjacent bond. Break the adjacent oxygen and carbon bond. And the remaining fragment will form the alcohol. Yes, Simda, tell me what will be the product in this case?
CH3, CH2, CH2I plus CH3, CH3, CH2, CH3, OH.
What you said, this group will form alcohol, CH3, CH2, CH2OH, you said, right? And this group, according to you, it will form the halogen, right? Halide group.
No, ma'am.
Ma'am, you said it correctly. So you said CH3, CH2. Basically, you said that this bond will cleave, right? Because this is oxygen linkage. This is your alpha carbon. Suppose this is your alpha 1 and this is your alpha 2. So alpha 2 is your tertiary. Alpha 2 is your tertiary. So you will attach the iodine to the alpha 2 carbon and you will break this bond, right? So when you break this bond, you will get CH3, CH2, CH2, and O and H. This hydrogen will get attached to this oxygen. CH3, CH2, CH2, OH. Your answer was correct. So, and here you will attach the iodine. C, CH3, CH3, CH2, CH2. Right, so that's your correct answer. Now for the mechanism part, we will do it in the next class. Tomorrow we will do the mechanism. Clear? Any doubt? Ali and Rimda from today's class?
Ma'am.
Okay, so I will try to complete this chapter by tomorrow. One mechanism, alkoxybenzene, aryl benzene, and there is one more part, the electrophilic aromatic substitution of anisole. And some commercial